All right, so last time we talked about what's the definition of V statistic. So to recall that, we started from the definition of, of an expectation functional. So this is how we define an expectation functional. Here, the y1 to ym are IID from a distribution f. Then you can regard this functional to be about some property of the distribution f. And then V statistic is defined as the plug-in statistic where we replace F by F and hat. And F and hat is the empirical distribution of a sample, a random sample from F. So X1 to Xn is an IID random sample from F. So then you see we can write this Vn as this expectation functional still, but f is replaced by f and hat. So now you see y1 to yn are just some general notations regarding IID random variables from a certain distribution. The distribution can be f or can be f and hat. And then given that f and hat is defined as a discrete distribution with point probability mass 1 over n at each of x1 to xm, then we can further expand this definition as this. That is, y1 to ym are just IID randomly sampled from x1 to xm. So here we denote that sample as xi1 to xim. And we consider all the possibilities. So here there are n to the power m, so many possibilities, and we do the averaging. And the averaging corresponds to the expectation here. And that's how we define VM. So here, one thing to remind you is that the definition of expectation functional requires G to be symmetric about its m arguments. That's something we assume, and we said that even if our G doesn't satisfy this, we can always create a version called G star that is symmetric across its m arguments, and that G star has the same expectation as G. So that's something we can define. So that's why without loss of generality, we just assume G to be symmetric, and we call this G a kernel function. Okay, so one thing we need to consider is that given this definition of Vn, it's possible that some of the xi1 to xim may coincide. They may get to be sampled from the same xi. When that happens, we will have some issue about the so we will have some issue about the expectation of Vn, because if we have two arguments here that are equal to each other, then that entry's expectation will not be unbiased. Okay, because the unbiasedness requires, going back here, the y1 to ym must be IID. So they must be independent. So how do we deal with that? We try to remove the cases where we do have replication or coincidence in those m entries. So what we did is that we defined the U statistic, which is here. So in the U statistic, we just remove the duplicates in those I1 to YIM. So that will make them all unequal to each other. And how many possibilities do we have here? N choose M. And so here we just add that constraint, only consider those xi1 to xim, that is, they are not equal to each other. And we take the average as still over all the possibilities, that's n choose m here. And obviously in this case, the UN's expectation is just equal to the TF, the parameter we're originally interested, defined by the expectation functional. So that's where we were before the Thanksgiving break. So today we're going to continue our discussion by giving you a concrete example about concrete example of a U statistic. So this example is what we call the Wilcoxon sign rank test. Okay, so this is the name. Rank statistic. So this is something quite widely used. It can be considered as a non-parametric paired two-sample test. Two-sample test. And it has the similar purpose as the paired two-sample t-test. So let's see what it did. So when we say paired two-sample test, we mean that our sample is paired. So we write our sample as x1, y1 to xn, yn. So we still have n IIDs, but here each observation in the sample is paired x1, y1, and xn, yn. So in this case, xi to x1 to xn, y1 to yn, they are all scalars. Okay. And here we define so because we're interested in whether the expectation of xi is equal to the expectation of yi. That's the question we'll try to answer. Question, or which we write as the null hypothesis, is the expectation of xi is equal to the expectation of yi. Okay, that's the question. And the alternative here we consider is that they are not equal. Alternative hypothesis. Then naturally, given that they're paired, we should look at the differences between yi and xi. So we define zi equal to, let me write it as yi minus xi for each I. Okay, and then we formulate the question as whether we can test the expectation of zi is equal to 0. Okay, so then we denote that theta to be the expectation of zi. Okay, with this notation, then the null hypothesis becomes theta equals 0 versus the alternative hypothesis is theta is not equal to 0. So we change the question to be like this. Okay, then how do we define the Wilcoxon signed rank test? Rank statistic. So we basically sort the absolute values of z1 to zn. Okay, so here is what we did. So sort the absolute values of z1 to zn as so in other words, here W1 represents the small W1 represents the Z1 after sorting. So still, I would say W1 to W2 to Wn is a permutation of Z1 to Zn, but they follow the order of the absolute value. So in other words, W1 to Wn is a permutation of Z1 to Zn. That's what we mean. And here the sorting is a little trickier, so that's why we didn't use the order statistic notation, because here we sort based on the absolute value, not the original values. Okay, then the signed rank statistic. Okay, here it comes. Wilcoxon signed rank statistic is defined as, use the notation Rn, is defined as the summation j from 1 to n, j times the indicator that wj is positive. So in other words, we go from following the order from W1 to Wn. And if that Wj is positive, we get indicator value being 1, and we get a sum, we get j into the sum. Otherwise, if it's negative, we will have a 0 in the sum, right? Because the indicator gives us 0. So in other words, Rn is the sum of the rank such that it's the sum of the ranks where the corresponding Wj is positive. So we only take the positive Wj and take their corresponding ranks and then take the sum. So then you can imagine what? If this null hypothesis is true, that is, the expectation of Zi is 0, then we can expect that the Zi, Z1 to Zn, they will actually take positive signs or negative signs equally with equal chances. So therefore, if you sort them by absolute value, we should still expect that the positive Wj should appear randomly in the rank list, right? That's something we will assume. And that's how we're going to derive the null distribution for this Rm. But for now, we just want to show you that to derive the null distribution, we can rewrite this Rn as a U statistic. So our later discussion about the asymptotic distribution of U statistic will be applicable. So we will show that Rn is a U statistic. Okay, how can we show that? It's based on the definition of this order, the sorting. Okay, so we can see that since we have absolute value Wi less or equal than absolute value Wj for I less or equal than j. This is how we sort. Then what we can say is that we would have Wi plus Wj greater than 0 if and only if Wj is positive. And this is the key. We can see why. Because no matter Wi being negative or positive, its magnitude is not large enough to cancel Wj, right? Because we sort them by the way, in the way. So that's why if Wj is positive, then we know for sure that Wi plus Wj will be positive. So therefore, we can see that another interesting result is that if we take the summation for I by letting I go from 1 to j, we would have, okay, let I go from 1 to j. Then we look at the indicator function, Wi plus Wj greater than 0. This is just by the equivalence, just equal to I go from 1 to j, stay here. I change the indicator to Wj greater than 0. And now you see I is no longer involved in the term being summed. So we just repeat this by j times. It's j times indicator Wj positive. And this is exactly what we have here in the definition of Rn. So we can rewrite Rn as the summation j go from 1 to n, stay here. I go from 1 to j. indicator Wi plus Wj greater than 0. Okay, so now we are closer. And, okay, sorry, I should make this is something I should make it clear. It's a U statistic asymptotically. So you'll see that later. So then how do we rewrite this as a U statistic? Wi and Wj are sorted, right? They are ordered by maximum, by absolute value. So they're not a Zi, Zj. But we know that each pair of Wi and Wj will correspond to some original pair among Z1 to Zn. And that's how we're going to take care of. So you see here, there's one thing we need to consider. That is, I could be equal to j. So we need to remove that from our consideration. So let's rewrite it. So we just separate the sum into two terms. So the first term is, okay, j from 1 to n, I from 1 to j minus 1. That's the first term, wi plus wj greater than 0. And the second term is when I equals j. J from 1 to n, indicator wj greater than 0. Okay. Now we see that for the first term, it's for sure about a pair of zi's, a pair among z1 to zn. And here, each wj must correspond to one of the previous z1 to zn. So we have both. And we can further see that. So about this term, right? So the first term, we can just rewrite it as j from 1 to n, I from 1 to j minus 1. We can still write it as we can now write it as zi plus zj greater than 0. As I said, the reason is that I can always find wi and wj corresponding to some pair among z1 to zn. And since they actually enumerate all the pairs, and I can actually do the same thing. So I see, so here, when I write it this way, I just didn't say, okay, zi equals wi, zj equals wj. I didn't say that, but there must be some correspondence between a pair here and the pair here. So I just use the original index to write the sum, and here is the ordered. Okay, and for the second term, I can also write it as, okay. So now you see that once we're able to do this, we are very close to the U statistic. You see that if I divide Rn by n choose 2, and I do that on both sides, so I have 1 over n choose 2, j from 1 to n, I from 1 to j minus 1, indicator zi plus zj positive. So, and the last term, you see, I would have, again, 1 over n choose 2, summation j from 1 to n, indicator zj greater than 0. So the first term is just our definition of U statistic. Okay, and what does it correspond to? What's the expectation functional? You can see that it's the expectation functional. So corresponding to this U statistic, the expectation functional is we can write it as indicator y1 plus y2 greater than 0. That's the expectation functional this U statistic is corresponding to by our definition. And the second term, you see, In the denominator, we have n choose 2. So it's in the order of n squared. But in numerator, it's just the summation of n terms, and each term is binary. So we can say for sure that the second term is just in the order of the order of 1 over n. Yeah. And here I use the notation big OP because it's a random variable. It's a random variable in the order of 1 over n. So that's why I said asymptotically, if we look at this Rn divided by n choose 2, this term, we can say it is asymptotically equal to un because the other term is going down to 0 in probability. Okay, so this is an example to show how U statistic can be very widely usable. Here in this Wilcoxon sign rank test problem, we show that its test statistic, after we divide it by n choose 2, it can be written asymptotically as a U statistic. So now the following discussion will be about how can we derive the asymptotic distribution of a U statistic. So by the definition of U statistic here, you see that it's not so easy because we cannot really apply the central limit theorem directly, since in the summation over I1 to IN, we know there are some repetition of the same xi being used in different terms in the sum. So that's why the terms are no longer independent as we require in the central limit theorem. And also so the only result we have given you so far that does not require the sum to be over independent random variables is the dependent M stationary sequence, right? We have that. But that M-dependent stationary sequence is not straightforward here. We cannot see how those things, those G's, give us an M stationary sequence. So that's why we need something better. We need to invent something, but can still allow us to use central limit theorem. Even the M-dependent sequence result was also based on central limit theorem, if you recall. Okay, so this is something we're going to introduce now. It's a very useful technique called the H projection. It's based on conditional expectation. Okay, so what is H projection? By the name, okay, so here the name H is actually from the person who derived this technique. It's called Hoffman, who has did a lot of things, useful things in statistics. So like the Hoffman's test, right? Hoffman's test is a test for testing whether two random variables are independent, among others. So here we're going to talk about his other invention, the H projection. So what it actually means is this. So we define function gk, okay? So we define function gk. If we recall, our g function has m arguments, and we basically fix k of its arguments and only let the other arguments be random, and then we take expectation. So to be exact, the gk is defined for k arguments. Let's just take it as the first k arguments since g is symmetric. Defined as expectation of g with the first k argument fixed at y1 to yk, and only the remaining ones are random, yk plus 1 to ym. Okay, so in other words, you see, when we take the expectation, these things are the only random terms, random arguments to be taken care of. These stay as fixed. So that's what we mean. Okay, so now we can go general. So what if we replace these by random variables? Now we're actually under the conditional expectation scenario. So based on this definition, now if I allow y1 to yk to be random, then in this definition of gk, they are still fixed. So what this means is that I take the conditional expectation of y1 to ym by conditioning on y1 to yk. That's what I mean. So you see, this can be considered as a special case of that, right? So this is what? This is when I say, okay, the uppercase y1 equals lowercase y1, uppercase yk equals lowercase yk, then I will get this. But this is the more general way of writing it. So now I can see, I can still change my y1 to yk. They're random variables. But when I change them, they will only be reflected in the conditioning. So they will stay in my condition expectation. And yk plus 1 and ym here will still be taken care of by the conditional expectation. So just again, this is the general way, and this is a specific way. Here, I basically specify y1 equals y1, yk equals yk. Okay, this is what we call the H projection. So we basically created, you see, doing so, we can create what G1 to Gm. And Gm is exactly equal to what? Gm is just, so for G, so Gm is here. I conditioning on y1 to ym, and that's just G. That give me G. So the expectation is no longer there. Okay. So based on this definition, one thing we can actually see is that, so for k from 1 to m, one thing we can see is that if we further take expectation for y1 to yk in this gk, if we further do this, then we use the definition of gk. Maybe I should put it as definition. It's actually 2 layers of expectation. Okay, so the inner layer is the expectation for yk plus 1 to ym, and the outer expectation is for y1 to yk. So we know that from probability, these 2 layers will actually give me just the expectation of g, y1 to ym. Okay, so still, this is the expectation I'm interested in, right? This is how we define the expectation functional. That's our interest. And here, let's just give it a notation. Let's just call it theta. And we will just refer to this as the theta. So in other words, here we show that all the gk functions, by restricting just to y1 to yk, the expectation stays the same. Okay, and furthermore, I want to say that, so given the same expectation, let's define the variance of the gk at y1 to yk. So let's just give it a notation. So denote the variance still under the distribution f of gk y1 to yk. Let's define it to be sigma k squared. So this is a notation, and we're going to show it. So we're going to show that for the variance of the U statistic, it can be expressed by those sigma k's. That's the first important result we're going to give you today. So regarding the variance of U statistic. So let's call this theorem 1. So one thing we need to have is this. We need to have some requirement on the number of arguments in the expectation functional in relation to my sample size, x1 to xn. I need a sample size to be greater or equal than 2 times n minus 1. So when m is 1, right, for a lot of the expectation functional we are familiar with, like the mean, that is m equals 1. So this is just not an issue, right? 2 times 1 minus 1 is 1. M must be greater or equal than 1. That's not an issue. And for that case, the U statistic is just the summation of IIDs. We don't need to worry about the asymptotic distribution either. So the U statistic distribution only gets complicated when m is bigger than 1. So you see, when m is bigger than 1, when m is 2, we need n to be at least 3. When m is 3, we need n to be at least 5. So that's usually easy to satisfy, right? Because the sample size it should be large. Otherwise, it doesn't make sense to talk about asymptotic distribution anyway. Okay, then here, when this condition holds, the variance of the U statistic, I write it this way. So you know that in this section, we always carry the subscript f in our expectation and variance, so we know which distribution it's about. So this variance of U statistic can be written as 1 over n choose n, summation k from 1 to m. I let n choose k, m minus n choose m minus k, sigma k squared. So if you are familiar with the hypergeometry distribution, you have seen something similar. So this is actually n choose m is all the possibilities where we select m random variables out of n random variables. And here, this thing means that, okay, from the m variable, so we further select k from m, and we also further select the remaining m minus k from n minus m. So you see that this is a more restricted sampling. That means we first divide the n into two parts. One part has m random variables, the other part has m minus m random variables. And from each part, I draw randomly sample k and m minus k random variables to make up m random variables. So that's how we do it. And okay, so let's look at how we can show it. So if we can write this, okay, a very natural result is if sigma 1 squared to sigma n squared, right? Because k can be as large as n, are all finite. Then by simple algebra, do some cancellation by looking at the orders here and the order here. By order, I mean order of n. Then we can see that this variance is equal to m squared times sigma 1 squared times big O 1 over n, plus the remaining terms are big O 1 over n squared. So you see that you see here, the interesting thing is that in the summation, okay, as my k gets larger and larger, then what I would have is that the order of n is getting smaller and smaller. So once I do the cancellation, so I cancel the n in the denominator and the n in the numerator for each term, I can actually see that I'm dominated by the first term. And the first term is just sigma, the term of sigma 1 squared. So in that case, k is 1, right? So m choose k is m choose 1. I get an m here, and here I have n minus m choose m minus 1. So I also have a lot of things to choose from here. So basically, after some cancellation, which we'll see later, I get the order of 1 over m. And I can show that the further terms are actually of smaller orders. So asymptotically, you see the natural result I obtained from this theorem is that I only need to worry about sigma 1 squared as its asymptotic variance. Okay, so let's see how we can show this result, why it holds. So to prove this, we first need to actually worry about the terms here. Okay, so let's look at the variance of un by multiplying n choose m. So I get rid of the denominator. So this is equal to the variance of, if you still recall the definition of the U statistic, 1 less or equal than I1 less than IM less or equal than M. G xi1 to xin. Okay, and now we can talk about some overlap among those terms. So let's consider K to be the overlap of two terms. So let's say by overlap, I mean that the xi1 to xin get to pick the same random variables from the original sample x1 to xn. So here they may overlap by one random variable and they may overlap by n random variable, right? So we can have all those possibilities. And so therefore, you see that I'm going to talk about, so here, let me see it. So I can write it down and then I explain it. So we have n choose m, and we let k go from 1 to m. M choose k. M minus n choose m minus k. And the covariance of g y1 to yn and g y1 to yk, ym plus 1 to ym plus m minus k. Okay, so this is actually the definition of the covariance. So you see that how many terms I have in here. The number of terms is equal to n choose m. Okay, so I can have n choose m terms in the summation. And for those n choose m terms, when I write out I expand the variance, it becomes the pairwise covariance between two terms. And how many possible covariants do I have here? So first of all, the covariance could be, so if it's just so you know that it will be the pairwise, or I should say it'll be the pairwise covariance and the variance of each individual term. So then you see that when k is equal to m, then I would have this term exactly as the variance of g1 to gn. Oh, as x1 to xi1 to xin, I should say. The variance will be that. And otherwise, if between two terms, I need to consider their overlap. And the overlap here is basically, I just call the first k terms to be the same. And the remaining m minus k terms, so I refer to it as ym plus 1 to ym plus m minus k here. While over here, it's just yk plus 1 to ym. So I have different n minus k terms in the later half, and I have the same k terms in the first half. And you may wonder what happens when I do not have any overlap. That in that case, I would have zero covariance, right? Because of IID, because of independence, the covariance becomes zero. So I only need to worry about the covariance when there is some overlap between the two terms. And that's how we write it out. So you see, when they have K overlap, then the question becomes, I choose K from the M to be the same. And then the remaining M minus K are chosen from M minus M. And here I let them to be different here and different here. So ultimately, what the reason I have here is that, let me see. Yeah, the reason I have this summation is that I still need to choose n random variables from x1 to xn, right? But when I choose it, then for those terms in the middle, I will have many possibilities. And I just count the possibilities by considering the overlap k. So for k equals 1, I count how many possible ways can I get there. And for k equals 2, I do the calculation up to k equals to m. When k equals m, the covariance becomes the variance. So that's how we write it out. And then it remains to show what is this covariance. Okay. So to show this, let me just rewrite it. So to show the covariance, maybe I can set it in a clearer way. So for the first term, I have y1. Yeah, so for the first term, I have y1 to yk and yk plus 1 to ym. That's the first term. And the second term, they overlap y1 to yk, but the second half is changed to ym plus 1 to ym plus m minus k. Okay, that's the covariance between the two things. And how do we calculate it? Again, we are going to use the formula we are familiar with. That is the expectation of product. So let me just give it a notation. Call this as 1 and call this as 2. So it's actually equal to the expectation of the product minus the product of expectation. Okay. And then what is the expectation of the product? Again, we're going to use the Tower rule to help us show it. So for the expectation of product, what we're going to show is, okay, so let's look at the definition of expectation. We're going to use the Tower rule, so they share y1 to yk. So I can write it as 2 layers of expectation. So in the inner layer, I write it as the product given y1 to yk. And then I use the outer product to take expectation of y1 to yk. So given that they share the same y1 to yk, you see, what do I have? So I'm just in the case of, so when I'm conditioning on y1 to yk, you see that they actually become independent, okay? Because I'm in the inner expectation, I'm taking expectation just for yk plus 1 to ym and ym plus 1 to ym plus n minus k. And these things are independent. So you see that what I would have here is for the inner product, I can separate them into 2 expectations. It's actually equal to expectation of 1 given y1 to yk times expectation of 2 given y1 to yk. Okay, and the reason I could do this is because yk plus 1 to ym and ym plus 1 to ym plus n minus k are independent. In the inner expectation, my y1 to yk are already taken as constant. So that's why I don't need to worry about them. Okay, and now you see I have something nice, right? Expectation of 1 given y1 to yk is exact my definition of gk. So you see, here I just get gk y1 to yk. And same for 2 times gk y1 to yk. Okay, and this is what? This is the expectation of square, right? It's the gk square. And I know this is equal to the variance of gk y1 to yk plus the square of the expectation of gk. And okay, and we have notation for both. This is just what we denoted as sigma k squared. This expectation is what we call theta squared. Okay, so I'm good. I get this expectation of 1 times 2. And then for expectation of 1, we know it's theta. Expectation of 2, we also know it's theta. So then coming back, so if I go back to here, so this will give me sigma k squared plus theta squared minus theta squared, sigma k squared. So this covariance is just equal to sigma k squared. And that completes our proof. So you see, this is what we wanted to prove, and here, this is how we did it. So there's nothing fancy here. The only thing we used is the expansion of variance for sum. We basically expanded to be pairwise covariance between two terms, between every two terms in the sum. And that's how we did expansion. And that's how we get here. Okay, so now let's take a look at I think I'm going to skip this derivation. It's algebra. So what you need is to, when you have this, right, you expand the factorial. You expand the combinatorics number into factorial. So what is n choose n? It's actually n factorial divided by n factorial divided by n minus n factorial. And you do the same thing for this number and this number. And you cancel whenever you can for terms related to n. And you count how many terms do I have for n in the numerator and in the denominator, and you will see this immediately. So I'm going to skip this part. But then you see that this gives us a very promising and simplification. That is, to worry about the asymptotic distribution of U statistic, we only need to worry about sigma 1 squared. And that's so nice. Okay. So that's the first result. And the second result we are going to give you is that we're going to talk about another, I would say, surrogate for U statistic for us to prove the asymptotics. Okay, so let's consider a surrogate. And we define this as UN tilde. And this definition is defined as I from 1 to n. So this is based on our sample, random sample, expectation under F of UN minus theta given xi. So UN is still our U statistic, but now we're taking U statistic minus its mean, right? This is the mean. And we're doing it for conditioning on xi. So this is an important thing we need to understand about conditional expectation. So once we do the conditional expectation, so what we get out of it is still a random variable. So this is still a random variable. But if this random variable's randomness is only from xi, a random variable whose randomness is from xi. That's the definition of a conditional expectation. And then you see here we have n terms, and each term is a random variable depending on xi. Because xi's are IID, then we have independent terms. Okay, we have IID terms. So in other words, you see here these terms, so this is a sum of n IIDs, IID random variables. This is what we have because the xi's are IIDs. So that's why you see here for this term, for this thing, we can apply central limit theorem. So for this one, we can apply central limit theorem. And we will use this central limit theorem to finally obtain the central limit theorem for un, and we'll see. So see here that to apply central limit theorem to un tilde, what the only thing we need is the variance of each term in the summation, right? So we know that in order to write, that is, we can write as, okay, root n times 1 over n un tilde, right? And minus its mean. Here clearly we see because un is unbiased, by taking expectation of un tilde, it's 0. Minus 0, converge in law to normal distribution, mean 0. And here the variance is the variance of each term. Okay, we will need that. The variance of f un minus theta given xi. Oh my bad. I need the expectation f. Sorry, expectation that. Yeah. So that variance is what I need in this asymptotic distribution. So now I need to calculate this. What is that? So then the question is, what is the expectation of un minus theta given xi? I need to know this so I can calculate its variance. And this is we call this a lemma in the notes, but I'm just going to just do the calculation here without calling it a lemma. So in order to show this, we need to go back to our definition of the U statistic. So recall the definition of UN. So with the definition, we can write expectation of un minus theta given xi as if you recall, it's actually here it's the 1 over n choose n summation I1 to In. They are less than each other, they're ordered, and then expectation of gxi1 to gxin. That's my definition of un. And here I can basically I can write out the un and take the subtraction into the summation. So here I would actually have, let me just write it out. Okay, expectation of g xi1 to xim minus theta given xi. Okay, So that's how we just the definition of UN, and we take the subtraction and then we do the conditioning because we can move the expectation inside the summation. So that's how we do it. Okay, then what's this expectation? It's interesting, right? So it depends on whether my xi happens to be one of the xi1 to xim. If it is, then I would be conditioning on that xi. So I'm actually in the scenario where I'm conditional on one of the in argument, and that's g1. That gives me g1 xi minus theta. If xi is not one of them, then by independence, this conditioning can go away, and I will get 0. So you see that for this term, I need to consider two cases. So it's either g1xi minus theta if I is among I1 to IM, or it's 0 otherwise. So I just consider those two cases. And for how many cases can I have xi among one of them? So how many cases can I have I among I1 to IM? That's when I choose those M things. I first choose xi, and then I randomly pick M minus 1 from the remaining M minus 1. So you know that here the possibility for this to happen is just M minus 1 choose M minus 1. Because I don't need to choose xi. Xi is in there. And divided by n choose m times g1 xi minus theta. Okay? And then I just need to do cancellation here. And I can easily show that this is equal to m choose m g1 xi minus theta. Okay, that's this. I obtained this. So now what's left is to show the variance for this term. So then the variance f of expectation f un minus theta given xi is equal to, you see, I'm going to do this, is equal to m squared over n squared. And let me see if I'm right. Expectation of that minus theta. Yep, I think everything is right for n. Okay, so that's the variance of f, and because this is equal to g1 xi, that's it, because minus theta doesn't change the variance. So I'm left with m squared over n squared sigma 1 squared. But let me see, why do I have n here? That's something I need to get away from this central limit theorem result. Let me see. g1 xi minus theta. Sum of independent, yeah. It seems that everything's right here. UN tilde, this is the sum of expectation, right? Each one is IID, and then I just need to get a variance for each term. Oh, I see. I think I know what's going on here. My bad. Okay, sorry. Okay. So this is okay. This is okay. So these things are all correct. And now, so with this, okay, let's come back to the UN tilde. Okay, so then we see that. I think I was too quick here, but let's rewrite it. So then the UN tilde, by this definition, I from 1 to n, by this result is actually equal to m over n g 1 xi minus theta. Okay, and then I move the n out of the summation. Okay, so I would have 1 over n, the n comes from here. I from 1 to n times g1xi minus theta. So I'm going to apply central limit theorem to this, not this, okay? So what do I do? So you see, by writing out this, then this will become, I know by central limit theorem, they are IID. So this by CLT, the central limit theorem applies to U tilde n, and itself is an average of IID. Yeah, this is where I should apply central limit theorem. Average of IID. I would have root n times U UN tilde, okay? Root n times UN tilde. This will converge in law to normal distribution because it has mean 0. I don't need to do minus 0 here. And then the variance is about m times g1xi minus theta. Yeah, that's what I have. And then you see that this is equal to m squared sigma 1 squared. So that's why here the result is like this. So this is not right because I have some issue here since this term itself is an average. So I don't need to do average further. So don't just forget about this. Yeah, but this was my thought. This was the idea so that we need to calculate this. But after seeing that, we don't need to go this route. We just need to go this route. So by writing out the UN tilde itself as an average of IID, then we apply central limit theorem directly to U tilde n. Okay, so that's what we have for the U tilde n. As I said, it's a surrogate. It's not UN. But finally, our result will depend on the fact that the UN minus theta and U tilde n, they are asymptotically equal. So finally, we want to show that the root n of the UN statistic, U statistic minus theta, is converging in law to the same distribution, normal mean variance m squared sigma 1 squared. So we want to show this And then with this, we finally have the asymptotic distribution of U statistic. And how do we do it? We're going to apply Slotsky theorem. If you recall, in Slotsky theorem, we have that if we have two random variable sequences, if their difference is convergent to 0 in probability, then those two random variable sequences will converge to the same distribution. That's it. So to show this, we will show that root n of un minus theta minus un tilde is converging in probability to 0. That's what we're going to show. Okay, and now to show something is converging in probability to 0, here, because by the definition of un tilde, we already know it can be written in terms of G1xi, the Hoffman projection, the H projection. So then it's easier actually to show that this difference is converging quadratically in quadratic mean to 0. So we have the Rth mean convergence that implies convergence in probability. And that's also something you use in your homework, right? To show an estimator is consistent. And that consistency is defined by convergence in probability. You can actually show that estimator's variance is going down to 0. Then by Chebyshev's inequality, you would have convergence in probability in that case. And here, similarly, we want to show that we can have quadratic mean convergence to 0. That would imply convergence in probability to 0. So then we want to show it is sufficient to show that the expectation of root n un minus theta minus un tilde. To show this thing, I would say, maybe better. The expectation of the square is going down to 0. Okay. And in order to show that, we can actually do two things. The first thing we want to show is, so this left-hand side, let's do the expansion, okay? So we can get n out. And then inside expectation, we would have expectation of un minus theta square. That's the first term. And then we will have minus 2 expectation of un minus theta times un tilde. That's the second term. And last term is expectation of un tilde square. Okay, that's what we do for the left-hand side. And for the first term, because we know un is unbiased, right? When it's unbiased and its mean is theta, the first term becomes variance of un. That's the first term. And the second term, we need to calculate it. We don't know yet. And the third term, we just keep it for now. So now what's the second term? The second term, let's look at it. So this is a little tricky part. So for the second term, we use a new page to write it. So this is also a lemma we have in the notes, but here we are talking about it in the reverse order. So when you read the notes, you will see more clearly. So it's the expectation of the product of un minus theta and un tilde. And un tilde can be considered, as we said, a surrogate for un minus theta. And un tilde is already known, right? Un tilde, we already did the calculation, and it's 1 over n summation of this. Okay, so let's do the expansion. So un minus theta stay here, and let's talk about un tilde. And here un tilde, if we write it out here in terms of summation I from 1 to n, it's n over n g1xi minus theta. Okay? And then we can take the summation out. We can take the constants out of expectation. So it's n over n summation I from 1 to n. And inside the summation, we have expectation of un minus theta times g1xi minus theta. Okay, now we're going to use the conditioning trick again. Because if we do not do that, this seems to be too complicated, right? If you think about the definition of un, it involves all the possible xi's, right? And that's very difficult. So we are going to do conditional expectation again. So this is the outer one, and in the inner one, we have un minus theta g1xi minus theta conditioning on xi. Okay, now again, you see, it's easier. We can get this out of this inner expectation. So this term, the inner part, is equal to g1xi minus theta, just times expectation of un minus theta given xi. And what is that? We know it, right? So we actually did the calculation here already. This is exactly what we did. Un minus theta given xi, conditional expectation, is equal to m over n times g1xi minus theta. So I would have m over m times g1xi minus theta squared. Okay, and then you see I can do a lot of simplification. I move this constant out, and then I just get m squared over n squared times the summation I from 1 to n, expectation of f g1 xi minus theta squared. That's what I have. And I know this is the expectation of a square. So I know that here g1xi is expectation of theta. So again, this is the variance. So it's m squared over n squared. It's the variance of g1xi. And by our definition, this is just sigma 1 squared. And we have n copy of that, so we cancel 1n. We get m squared over n sigma 1 squared. That's it. So you see, we have largely simplified this calculation. So then moving back to here. Moving back here, we can see that this is minus 2 times m squared over n sigma 1 squared. That's what we have for the second term. How about the last term? So the last term, you see, by our definition here, by our calculation here, it's already very obvious. its variance is simply this. So what we have is this is equal to m squared sigma 1 squared over m. So that's also the variance of u and tilde, because the variance here of each term is m squared sigma 1 squared, and we have n such terms, and we have this 1 over n outside. So for variance becomes 1 over n squared. So 1 over n squared times m m squared sigma 1 squared. So we have that. So you see, we can cancel one copy here and here. And for this one, we have previously derived that, if you still recall, from our earlier result, that theorem is equal to m squared sigma 1 squared big O 1 over n. Okay? So now you see we have this plus this minus this. And we can see that this is coming down to 0 for sure, because we would actually have, yeah, right? So we would actually have, so this is equal to 1 plus n, yeah. So expectation of u tilde n squared. Yeah, so we actually have, is it right? The 1 over n is here, 1 over n is here, 1 over n is here. But what do I need is variance of this big O1. Okay, sorry. I think my bad. Yeah, this is right. And then I have I need to go one more term. Yeah, that makes it right. So big O 1 over n squared. I need that term. So then you see, basically what I want to say is that, so for the order 1 over n, this plus this canceled out this. So that term goes to 0. So I'm left with n times big O 1 over n squared. So I'm left with big O 1 over n. And this is going to 0. So that completes the convergence in quadratic mean. So now with convergence in quadratic mean, I can have the convergence in probability. And then finally, I have the un minus theta times root n converge to the same limiting distribution as root n times un tilde. And that's why I can finally obtain this result. So this was a long derivation, but I hope that it's not, so I hope that you understand the essence here is that we are trying to use conditional expectation. That's what we call H projection. So using conditional expectation, we were able to find a surrogate for this target, the root n un minus theta. We find this surrogate as the root n un tilde. And for this root n un tilde, we could apply central limit theorem. So that's the basic idea of proving deriving the asymptotic distribution. So un tilde is our key step. And furthermore, we want to use the H projection to simplify the variance of un. And that's what we did earlier. So to simplify the variance of un, we were able to show that we only need to care about the first term asymptotically. And that's just the variance of G1 YK. And that's much easier. So we don't need to worry about sigma 2 to sigma m. So you see this idea, we also used it in our m-dependent stationary sequence result. So asymptotically, we can simplify a lot of things by dropping terms that are too small. Okay, so we'll stop here. So we have obtained the main result for the asymptotic distribution of U statistic. Again, as I said, if in the definition of U statistic n equals 1, that is the expectation functional has only one argument in the g function, then we don't need all of those. Central limit theorem just gives us the result. But we need this when the g has more than one argument. So we will give you some example to show how this can be useful in practice in our next lecture. Okay, so see you on Thursday.